Welcome, everyone. Welcome to the practical session of high resolution TEM. I will, let's say, host this session, but it's not only me. Now I'm in the office. We organized this session to be presented from two spots. My colleagues Raluca and Adrian are at the microscope, and that will be one location from which we will broadcast, and then from the office. So we will there will be a parallel transmission from two spots. Allow me to start this practical session by launching the promotional video that CERIC realized for this event, and I will launch the film that you have, that you can see also on YouTube. And I will just a moment. I will do share screening for screen sharing. Sorry. Sorry for interrupting. Can you hear it? Can you hear also the sound?
No.
No. Okay. So I will do that again, because that will be important for the other things that I would like to show you during the demonstration. Wait a second. Okay. Optimized for video clip. Can you hear it now?
Yes.
Okay, so we'll
Yes.
continue. In transmission electron microscopy, or TEM, we use a beam of accelerated electrons to study the internal structure of micro-objects. The instrument consists of several main parts: an electron gun, electromagnetic lenses for shaping the electron beam, and specialized detectors for recording the scientific data resulting from the interaction between the accelerated electrons and the thin specimen that they pass through. Therefore, specialized techniques have to be applied to obtain samples with a thickness of a mere few tens of nanometers. High-resolution transmission electron microscopy, or HRTEM, is a TEM working mode meant to visualize the atomic structure of crystalline materials. The thin sample is inserted in the way of the electrons accelerated by a high voltage, typically between 100 and 300 kilovolt. Electrons emerging from the sample carry information regarding elastic and inelastic atomic interactions experienced while passing through the sample, and can be used to generate enlarged images of the internal structure of the samples, electron diffraction patterns, or spectra revealing the local chemical composition of the sample. HRTEM addresses solid-state crystalline materials in various morphologies: powders, thin or thick layers on various substrates, or bulk materials like ceramics or metallic alloys. Beside the typical imaging and electron diffraction capabilities of a TEM, the nowadays instruments are complemented with highly sensitive analytical systems, like the EDS and EEL spectrometers. Apart from HRTEM imaging, the instrument installed in our laboratory offers several other imaging, analytical and combined working modes. The scanning transmission electron microscopy, or STEM mode, is available at a spatial resolution below 0.1 nanometers due to a spherical aberration corrector inserted in the microscope column. Combined with the EDS spectrometer and the post-column EEL spectrometer, we are able to obtain local chemical and structural information with a space resolution down to atomic scale. Considering the atomic resolution imaging capabilities and the analytical techniques available on our complex instrument, we are able to perform advanced microstructural characterization in a wide range of research domains, from nanotechnology, including nanomaterials and thin films for microelectronics, to metallurgy, ceramics, and other complex materials for the nowadays applications. Although HRTEM refers to visualizing the atomic structure of materials, it is not possible to use this technique for imaging single atoms. However, this can be done in certain conditions using the aberration-corrected STEM mode. The imaging principle in HRTEM is based on the interference between the diffracted electron beams emerging from a crystalline specimen. Therefore, it is not possible to see the atomic structure of a single molecule. Moreover, it is not possible by any electron microscopy technique to observe the atomic structure of amorphous materials, like glasses or polymers. Okay, so I will stop here. And hope you can still hear me. And then I will like to present you, before going to the microscope, I would like to present you something about the specimen preparation. I ended the presentation this morning with this chapter. Now I would like to show you how it looks like in practice. And we recorded the main steps of sample preparation for two types of samples, powders and thin films. And I will launch a short movie. And I will share it. Wait a second. I hope I had the same. Share. Yes, so you should hear also some sound. So I will try to also comment this movie as we are watching it. So we are heading now to the samples preparation room. This is a general view from the sample preparation room with different tools for different operations that I will try to describe as we will see the movie. And as I said, we can prepare and observe different types of samples, from powders to ceramics and metals, and we will illustrate with the preparation of a powder sample. This is my colleague Dana Radu. She will prepare a powder sample for TEM. So the sample will be deposited, let's say, on this TEM grid. We use a small quantity of powder. So that's the way she does it. So now she will crush this powder into very fine powder. This is alcohol that she used, and now she will disperse the crushed powder into even finer. So she will try to separate the fine grains that she created by crushing, by using ultrasound machine. And this is the TEM grid where she will drip 1 or 2 droplets of liquid suspension. And that was it. So the sample can go now to the microscope, which is not so simple for thin films, for example. So we have to prepare some sandwiches, and we start by cutting the sample into small pieces that we assemble together, and you will see the main stages. So we have to cut small pieces, and we use for that this wire saw. We have a saw of diamond here with diamond grains. And so my colleague cuts small pieces like 0.5 millimeters thick. The length is about 3 millimeters. So she needs to cut at least 2 such small pieces that she will now prepare for assembling into a sandwich. So these 2 smalls, they are 3 by 0.5 millimeters. So she used a small droplet of a resin, of a special epoxy resin. So now she created a sandwich. We have to put this in the oven for the resin to get solid. And after gluing, we will use this tool, which is called tripods. So we have to glue the sandwich on that mobile piece of the tripod. And then we start polishing the sample. This is how it looks when it's on the tripod. And now we start polishing the sample on both sides of the sandwich. First of all, the first face should be very smooth, and then we remove the sample and we turn it on the other side, and we continue polishing and thinning while being on the other side of the sample. So now she turns the sample on the other side. So in the end, we will have a thin sample, something like 100 microns, with both side faces very smooth, onto which, before removing from the tripod, we have to add a copper ring like that. We remove it then from the tripod, and we go to the next step, ion milling. We use this tool to install the sample onto the specimen holder of the ion milling machine. Now the whole operation is very delicate. The sample is about 100 microns thick. We have to be very careful not to break it. Now it is installed in the ion milling machine. So we use here two guns of ions, two ion guns, to send ion beams to the sample. We can control the angle of incidence, the accelerating voltage, and we continue the process until, while monitoring through an optical microscope, until we create a small hole into the sample. So now the sample is removed. So the reverse operation, she removes it from the mounting tool. Of course, the sample is even more fragile now because it is in the thinnest areas below 50 nanometers thick. She has to do it very carefully, so she puts it into a capsule. And that was it for the cross-section preparation. These are some other tools that we have in the lab, for example, to deposit a layer of carbon. For example, for the situation when we prepare ourselves the carbon membrane for the powder samples. So the carbon membrane is not what we do, is not a pure carbon. Of course, you can buy from specialized providers pure carbon membranes, but now here we have some a plastic membrane onto which we have to add some carbon in order to avoid electrical charging during TEM observation. This is another tool that we use to cut discs of 3 millimeters. It's an ultrasound cutting machine. Here is the cutting head. These discs are then polished using this simple device, but very effective. So instead of the tripod, we use that device. And we end the mechanical processing with this machine, which is called dimple grinder. So we create some concavities. Another tool to cut small pieces from bulky samples. This machine here is used for embedding samples into a special resin for SEM investigations, polishing machine, electro-polishing machine. Okay, so thank you for watching this short movie that we did prepared in our lab. I will try to follow what the schedule that I prepared here. So I will go slowly to the electron microscope, and I will run another small movie introducing our microscope and the colleagues who are going to be our host at the microscope. And just a moment. I will share this one too. What am I doing? Sorry. I will try to do it again. Oh, come on. Share. I will do it again from the beginning. So this is the room of the ARM 200F microscope with my colleagues who will do the practical session, Raluca here and Adrian. And from now on, I will pass the microphone to my colleagues who will enter in. I hope they can hear me. Yes, they are active.
Hello.
So they will, so you can see Raluca, and I will stop
Hello,
talking.
can you hear me?
Yes, we can hear you. And so she will install a sample and we will examine it together in the microscope, and she will describe the operations that she's going to do. I hope you can see her and not me. Anyway, I will mute my microphone and stop the video, perhaps to help you seeing only what happens at the microscope. So I will let her talk.
Yes, here is the sample. It's very small. I don't know if you can see. Okay. First of all, here is the holder. And I have to remove this small piece which will hold the sample here. Okay.
We have recorded this operation, and I will show you to see in detail what she is doing there, while the sample will be under at the plasma cleaning and before inserting it into the TEM column.
Now it's okay. We have to check it a little bit. Okay. Okay, now we'll go at plasma cleaner. Okay. Okay. And now we have to wait a little bit for the vacuum, and we'll apply the tension, and after that we'll see the plasma inside.
I'd like just to add what is the role of this plasma cleaning. Although the sample has been prepared using, let's say, very clean procedure, I mean the ion milling, in time, if you don't go straight from the ion milling straight to the microscope, in a few hours, let's say, you can already collect on the sample surface traces of hydrocarbons, which are nothing else but a source of carbon contamination in the microscope. When you use a focused beam, especially when you work in STEM and you focus the beam on your sample, you decompose the hydrocarbons that are on the samples on the surface of the sample, and they are not completely removed from the sample, but they are partially decomposed, and you start building up a carbon layer on your sample. This is called the carbon contamination, and this applies every time you use a focus beam, even in SEMs. But in an SEM, the situation is not that critical, because you still the created layer of carbon is not very thick, so you can still have information from underneath, from the sample itself. But when you want to obtain atomic level information in the STEM mode concerning the structure, the atomic structure, and the chemical composition by yields, each additional layer of carbon masks the information coming from the useful information coming from the sample itself. So we have to avoid as much as possible the formation of this carbon layer. And this is why we apply this plasma cleaning, which sometimes is not even enough. Even after plasma cleaning, we still have carbon contamination in the microscope. So there are other procedures that we apply in the microscope. And even in that case, if we don't manage, we take the sample off, we reinsert it in the plasma cleaner and put it back in the microscope. And so what I want to understand is that the nice images that you see in the papers, in the scientific papers, or what I've seen you, what I've shown you this morning, they are not quite immediately obtained. So for such images, there are sometimes situations in which you have to go to the microscope several days in a row, and perhaps in one day you will have the necessary luck, and you will get the nice image that you can publish. So that's what I wanted to add.
Okay. We can apply the current.
I don't know how close you can get with the camera to show you what. Now you can see here the plasma. It's an air plasma, so it's not. There are different types of machines. This machine works with atmospheric air. So the role of the plasma is to remove the layer of hydrocarbon which is absorbed on the sample surface from during the time from the preparation till the TEM observation. So we keep it under the plasma for a few minutes, and I will take advantage of this short break, and I think I will show you a little bit around the microscope. Or Adrian, perhaps you can show us around the microscope because you are.
Yes.
So of course, the main part is the microscope column. From top to bottom, we have the electron gun at the top, which is a field effect gun, a Schottky type, which means there are two types of FEG electron guns. Field effecting gun, Schottky type, which means that the filament is still heated, and there are also cold FEGs, cold FEGs, in which the filament is not heated at all. So we have a warm FEG. Then we have the condenser lens system. Then we have the aberration corrector. And here in the middle of the column, you can see a compartment where we are going to insert the sample. We then have so the sample will be inserted here, and then below the sample, actually the sample goes into the pole piece. The objective lens has the objective lens, and every lens along the column are electromagnetic lenses. They are nothing else but special coils, and each of them has a special pole piece, and our sample goes between the two poles, magnetic poles of the pole piece of the objective lens, and then we have below it two other lenses, an intermediate lens, a projector lens, and the fluorescent screen. At the bottom of the column, we can see the fluorescent screen through this window here. The whole column is under high vacuum. We are at about 10 to -7 millibar, so it's 10 to minus 5 Pascal. What else we have around the column? Right behind the column, we have the high voltage source. Adrian will show you so this is the high voltage source. This is where the 200 kilovolt are created, and they are applied through this cable, high voltage cable, at the electron gun level, right on top. This is a very delicate cable. You can imagine that it has to cope with 200 kilovolts and not to have any leakage at this high voltage. Next to the high voltage tank, we have the electronics for the CS corrector, for the aberration corrector. Okay. Next to it, we have some other electronics for the vacuum. Here inside, we have the EDS detector, which can be removed from the column, and so we have it is cooled with liquid nitrogen. All the other accessories like CCD cameras, only one of them is visible. He will show it to you. The Orias Gatan camera, which is this one here below. Yes, this one here. There are two other cameras which are not visible. They are under the column. They are specialized for. This is let's say the working horse. We use it to observe and to record low magnification images and diffraction patterns. And all the others, one of them is for recording high resolution TEM images, which is under at the bottom of the column, but we cannot see it. It is masked by a panel. And also a third camera, which is at the end of the EEL spectrometer, to record the EEL spectra, but also energy filtered images. Okay, so now the sample is inserted. I will probably show you in a short video what Raluca did when she mounted the sample and how she inserted the sample into the microscope. Okay, just a moment. Where is it? Why I don't see it? Okay. There it is. So the sample is in this little capsule here, and she has to install it under the small piece that she removed. This sample, this specimen holder is called a double tilt holder. So in an electron microscope, you need sometimes, depending on the sample, but in this case, we need to be able to tilt, to orient the sample, to find a nice orientation, crystallographic orientation with respect to the electron beam. So we need at least 2 degrees of freedom. This is a double tilt holder allowing to tilt the sample along the axis of the holder and along an axis perpendicular to the holder axis. So we have 2 tilting axes. Both of them are operated by electrical small engines, electrical motors, engines. In addition, what you see here, these 2 small pieces are made of beryllium. That's why this holder is called also analytical holder. The beryllium holder is the beryllium pieces around the sample have a very low signal, EDS signal, so they don't come with additional signals that may arise from electron scattering around the useful around the investigated object. So of course the instrument, it's the holder itself is a delicate mechanism, but also our sample is a very difficult, very delicate object, and we have to be careful not to lose to break it, because otherwise we waste a whole time that we put to prepare the sample. So now the sample is in the microscope. The procedure we have recorded it also, because we installed the sample not today but 2 days ago, in order to limit as much as possible the possible carbon contamination. So after removing from the plasma cleaner, we have to insert the sample into the column, and the procedure is quite I will show it to you. So the sample is not inserted directly into the beamway. It is pre-pumped in a load lock, and then to equalize the pressures, and then and only after that it is inserted in the electron way, electron beam way. So this is how it's done. I will pass now the connection again to my colleagues, who will start the working session, the TEM session.
Stai un pic.
So you see that there are 2 layers of isolation. We want to have images at atomic resolution, and we have to isolate the sample as well as possible from the external factors like temperature variation, or sounds, or any vibration that will disturb the atomic resolution imaging.
Okay. Now we start the work. Unfortunately, we have to work with the turn off light, so I hope something in the screen. So at the beginning, we have to go in low magnification mode. I will we'll start to share screen because okay. I know. Well, because of the Zoom connection, we have some issues with the computer of the microscope, but we'll resolve this shortly. Yes, we passed it.
Okay, so I think you have this.
Yes.
So in view options, you should find something like hide video or something. You have an option of hiding this panel where you see the icons of all the participants.
Just hide video panel. Okay.
That should be yes. Yeah.
Okay. It's not working, but it's okay. It's okay. We can see here on the camera, we can see a hole. And at the edge of this hole is our sample here somewhere. So I will search for a very thin area to obtain nice high resolution images. So
we are looking at a cross section sample.
yeah.
And as you can notice, the big hole that you see in the middle of the screen is the hole created by the ion milling in the ion milling process. The sample is a bit is cracked, as you see. The upper part is you could see a.
Yes.
And
Here
now she went into the thinner. She would look into the thinnest part of the sample, and she will identify the layers. And
yes.
I will let her talk. Yes, please.
Yes. So here we have a substrate, the strontium titanate substrate. Here we have a thin film of strontium ruthenate. And after that, we have barium titanate. This is the ferroelectric thin film, and some small gold nanoparticles. And now we have to go into zone axis. We have to remove just a little bit the camera because it is a little bit dangerous to go in diffraction mode on directly on camera because it's a high intensity.
So as I told you, in order to have high resolution images, you have the first operation to do is to orient, to find a nice orientation of your sample. So we have to find an orientation along a main crystallographic axis, crystallographic direction, zone axis, as we call it in TEM. And we do that by inspecting the
electron diffraction pattern, and we try to orient the sample in order to have a symmetrical diffraction pattern. Now what you can see perhaps is a pattern which is not symmetric at all. We have a strong beam, which is the direct beam. And you see, as you can see, the whole pattern, the intensity distribution is not symmetrical around the strongest, the direct beam.
Yeah.
So, and what you can see, we can see, apart from the strongest diffraction, the direct beam, we also see some strong spots, which are nothing else but the trace of the Ewald sphere that you saw in the theoretical presentation. So the Ewald sphere crosses the point, the reciprocal lattice points, and those points which are crossed by the Ewald sphere appear as the most intense ones. They are like on a circle, passing through the direct beam. So now we have to tilt the sample in order to have a symmetrical intensity distribution around the direct beam, which is what Raluca is doing right now. So now you can see that the diffraction pattern is nice and symmetrical, which means that we have aligned the sample according to a main crystallographic direction, which can be determined by measuring and indexing the diffraction spots that we see here.
Okay. Here we have a selected area aperture. So the diffraction pattern comes from here, from this area, which means that I took an area including also the substrate and the thin films. I can introduce now a smaller aperture. Okay, and I will select just substrate. Okay. And this is my selected area electron diffraction from this substrate zone, or I can include also the thin films, exactly. So here we can notice some satellites. So just a second. The line.
So we are looking now at two overlapped diffraction patterns, one coming from the substrate and one or more from the thin films, because we have, you said 2 or 3 thin films on top of the substrate.
Okay.
So you, yes.
Acquire this electron diffraction in order to determine the crystallographic structure. Okay, here it is. Okay. And I will save this. Okay. I can put another selected area aperture and select just the thin film of barium titanate. And this is my diffraction, just from the barium titanate thin film. I will acquire the pattern and I will save it.
So in this case, we have an epitaxial film. So the diffraction patterns look very much alike. Of course, only by measuring them, you can decide which spots belong to which part of the sample, the substrate or the thin films. And you can also say something. You can say something about the crystallographic orientation between the substrate and the thin films, and so which is how the planes, the crystallographic planes, are aligned to each other.
Okay.
Only by analyzing the diffraction patterns. But you can also then, when you have high resolution imaging, you can also see how the atoms, how the structures are aligned to each other at atomic level.
For imaging, I will introduce the contrast aperture. And I will select the central beam, the transmitted.
If you could adjust a little bit the histogram of the image so that we can see the
already it is
shadow.
Yeah, I will increase a little bit the intensity of the beam. Oh,
okay,
something like this. This is it. Yeah, we can see the shadow of the aperture.
And she is centering now the aperture so that we have an equal number of spots on each side of the direct beam. So these are the diffraction spots, the diffraction beam, the diffracted beam, beams that we use to build the high resolution image. The idea is that all these diffracted beams are coherent to each other and they interfere. And the high resolution image is nothing else but an interference pattern between these diffracted beams.
Okay. This is our new image.
So this is how it looks after inserting the contrast aperture. As you can see, the image has now a better contrast. We can clearly see where is the substrate, what are the layers. We can see that there are defects in the film. We can see there are grains, we can see dislocations, and it's up to us to decide what we want to investigate from such a sample. So we can see, I think at the interface here, we see the strontium ruthenate layer, very thin, I guess. Here at the
Yes.
or you could show it, I guess.
Just a second. Yes. So here we have the strontium ruthenate thin film. It's very small. I think have a thickness of 25 nanometers. I don't know exactly, but we can measure. Less. Almost 15 nanometers. And barium titanate thin film have something like about almost 300 nanometers. Okay. Let's see.
In this particular case, when you look at this image, for example, you see a darker contrast next to the interface, and also defects crossing the thin films from the interface towards the surface. So this is what is called elastic strain contrast, because we have indeed an epitaxial growth, but there is still, however, a mismatch between the two materials. And the strain contrast that we see at the interface, it's a sign that the barium titanate layer is not completely relaxed, but is tensed, and it shows a different contrast, different diffraction contrast. The relaxation occurs through the creation of these structural defects, like dislocations that we have here. These are threading dislocations. But also you can perhaps carefully examining the high resolution images, you can identify mismatch dislocations at the interface between the three materials here. But this is a work you should do after. So the electron microscopy work has, of course, like any other experimental work, two parts: the data acquisition, and then the processing, the image processing, and the diffraction pattern processing, and the spectra processing. And so now this is an image at a bit higher magnification.
Yes.
I'm not sure I can see what's the magnification.
500K.
500,000 times. And perhaps we just started to see the atomic, yes, the atomic structure. So now it depends also what camera we use. As I told you, we have installed 3 cameras, 2 of which we can use in imaging mode. They are not at the same level with respect to the column. And the one which is at the column bottom, and we couldn't see it, it's called the Gatan Ultra Scan. This allows us to see, even at this magnification, we can obtain images where the atomic structure is clearly revealed.
Now we are at a magnification of 1 million.
Using the ORIAS
Yes.
cameras.
And I will go a little bit back. So now we have 1 million. And I will acquire an image. And after that, I will use the other camera to see the differences between. So, yes. Okay. Now we are at 1 million magnification, but with the other camera, which is at the end of the column. So we can see the difference. Okay. This is Orius and this is Ultrascan here.
Anyway, so you can also zoom into the images, and you can still see what's the difference between the two, and
Yes.
something else. As you can imagine, we are not in the best operating conditions. Working in live is not very. You cannot always obtain the best images possibly. But we wanted you to see a little bit how it looks like when
I will change the camera now.
when we are in real working conditions. I'm not so sure it's easy to see, but when I'm not so sure it's easy to show it, but when she operates, when she moves she changes the defocus of the objective lens, you might have a total reversal of contrast. And as I told you, this is one of the acquisition parameters that you are not very sure of. Of course, the microscope shows you a value, and you can take that into account when you analyze when you simulate the image. But from the HRTEM images, it's not easy to say if the bright spots are assigned to an atomic column or to the space between the atomic columns.
Yes.
So that's why if you really want to correctly assign the high resolution contrast to the atomic structure of the material, for example, here we have a different contrast,
Yes.
you have to perform image simulation trying to reproduce as well as possible the acquisition conditions. And for that, when you simulate images, you simulate them using different values for the acquisition parameters like objective length, defocus, and the sample's thickness. So the sample thickness is another unknown in this case. We don't know how thick is the sample crossed by the electron beam here. We just look at it, we see what the electrons see, but we cannot see the thickness. There is a technique in EELS to measure this thickness. But if you don't have an EELS instrument on spectrometer on your microscope, then you have no other choice but to simulate different images for different possible thicknesses and comparing them to the experimental images.
So now I'm playing with the defocus.
So you can
Now-
see how, yes.
Now I'm at minus 50.
Minus 50 nanometers. So we can measure this defocus in values of length, nanometers.
Okay, now nanometers with plus.
So this is plus 50 nanometers or something, no? Right?
4 nanometers.
Okay.
And this is 0.
Yeah, so sometimes the differences are not so easily observable, but that, yes, for example, here, this is completely different.
Yeah.
And you can clearly see the impact of the defocus on the simulated images. Sometimes the difference are consisting in a complete reversal of contrast. Which is not the case for the STM imaging mode, and we will see that in as a.
Oh.
You moved, you touched the microscope.
Yes, this is the effect of the noise. Okay. Okay. I will go at a lower magnification. I will acquire an image. Okay. I will use this image to show you how we can determine the crystallographic structure of a material using Fourier transform. I will choose this area. Okay. So this is it, the E50 of the substrate.
It looks very much like a diffracted, like a diffraction pattern, only it is just the fast Fourier transform of the area that she selected with the red square.
If I'm moving and I'm entering inside the thin film, it can be easily seen that the E50 is changing. So, and here we have the substrate again, and we can measure the spots here. Using this tool. So I will measure the distance between the spots. 2. Oh. I cannot see the value. Just a second. So this is the value. Measured here. And
So this measurement can be done either on live images, as she's doing now, or you can do it by on the recorded images.
yes.
And this is how you determine what crystallographic phase you have by measuring, by indexing and identifying the HKL indices, by comparing with the PDF files in literature.
Yep.
So by measuring all these spots and indexing, you are able to say what is the orientation, the crystallographic orientation of this grain with respect to the electron beam, and then with respect to a neighboring grain, for example, the substrate. Here we have the sample is barium titanate. I think.
Yes, but now I'm inside of the substrate, so it's
Okay.
strontium titanate. So it's
It's a perovskite with
and
cubic structure, and these are the typical distances. The lattice parameter is about 3.9 angstrom.
yes, this is 001. How I remember, and this have to be 011. And this one, without measuring, have to be 010. And this one, and this one to be clear, which, and this one.
Of course, these measurements can be performed either on the selected area electron diffraction patterns or on the FFT patterns. The advantage of the FFT is that when you have small areas, much smaller than the selecting aperture, you can have single crystal diffraction patterns like this by selecting small areas, which is not possible if the samples, if the powder has small grains, much smaller than the selecting aperture. If you remember how she did how she obtained the selected area diffraction pattern. So she selected an area, that's why it's called selected area, with an aperture. And there are 4 apertures on this microscope. But even the smallest aperture can sometimes be much larger than the features that we are looking at. And in that case, you cannot select a small area inside the strontium ruthenate layer, for example, which is only 50 nanometers thick. That's why FFT is very useful in these situations, and because it allows you to perform local structural analysis when you cannot do it by selecting areas with an aperture.
Yes. Or another way to measure the lattice fringes is to select one spot from the E50. Let's take this one. And
so she will apply a mask. She will block all the other FFT maxima, and she will filter back the inverse FFT of this pattern, which means that what we see now are only the fringes corresponding to the two selected FFT maxima. So it's a filtered image. It's a Fourier filtered image showing only these lattice fringes corresponding to the two selected spots. And we can easily measure now the lattice. So we are now back into the real space. On the FFT, we were in the reciprocal space.
Yeah.
So she can measure an average distance between the fringes.
Yeah. So here I have 2.85. Yeah, 2.81. 2.81 here. This one. It's a small difference between FFT and the filtered image.
Yes, so the errors are
yes.
We should take into account the measuring error, which depends very much on the magnification on which you recorded the image, because every pixel now in the filtered image corresponds to perhaps five or more
0.4
nanometers, angstrom.
Angstrom, yeah.
And in addition, this is a very local measurement that she performed in real space, while the FFT makes an averaging over the whole selected area. So it's statistically speaking, it's a more reliable value, let's say. But otherwise, of course, you can expect, especially when you are next to an interface or next to structural defects, you can expect to have significant variations of the lattice parameter due to the elastic strain.
I'm at the interface here, so you can see the spots are elongated.
Because also this is an overlap between two FFT patterns from the strontium ruthenate layer and the BTO, the barium titanate layer now.
Yeah. Okay. I will close this. Okay, we can pass at the other TM technique, STM.
I don't know.
It is something.
Would you like to have a break, everybody? It's to have a, I don't know, 5 or 10 minutes break. I don't know. How would you feel about this?
For me, it will be okay, a break. I don't know the others.
Yes, we can take a break.
Okay, because we can also move a little bit, and we come back, let's say, in 10 minutes, and we continue with the demonstration in the STM mode, and then the EELS and the EDS techniques.
Okay,
And
thank you.
Okay, so see you in 10 minutes.
Thank you.
Okay, can we start? Can we continue?
Yes.
Yes.
The participants?
Yes, yes.
Okay, so we continue. Okay. So I guess Raluca is now preparing to show us some STEM.
Yes. I'm searching an area. Good.
Okay, so she will change the operation mode. She will pass from TEM to STEM, which means that the electron optical lenses will be reconfigured for STEM in order to have a focused beam on the sample surface. So far, we had a broad beam illuminating a large area on the surface. Now we will focus it into a smallest possible spot, and we will scan it across the sample in order to get atomic resolution details, if possible. So there are a few steps to do that before having a high resolution image. First of all, she has to align the microscope to adjust the lens parameters in order to eliminate all the aberrations of the condenser lens system. Because all these aberrations limit the size of the spot on the sample. If you have aberrations, you cannot go below a certain spot size. So we have to eliminate them, meaning spherical aberration, the coma, the astigmatism, and we have to form the smallest possible spot.
Now I'm searching an amorphous area.
So this adjustment is done indeed onto an amorphous region of the sample, and the procedure is called ronchigram. So she has to, and you will see it, I guess, as she is going into an amorphous area at the border of the sample. Now you can notice this amorphous area looks like a perfect mosaic, and this is where she has to adjust this ronchigram and eliminate the aberrations that we can see. She's not very far from having a good shape of the spot on the sample.
I have a small contamination. You can see. Now I'm correct the comma.
Yeah, so these are adjustments that you have to learn how to do it when you learn how to work in STEM.
Yes. Okay, I have to center the bronchogram. Okay. So here we have a small contamination.
Yes, so the dark yes, stain that you can see now is the sign that we still have a little bit of contamination.
But it's not so bad. Okay, I will select this area for STM imaging. It's less affected by aberrations. So I will change the condenser aperture. I will choose a smaller one. Okay, I will make it. Tamdi. Okay.
So from that röntgengram that you had, that you saw a few minutes ago, she has to select only the central part of it, because the aberrations affect the border of this figure of the röntgengram, and she eliminates the aberrations by selecting only the central part. As in optical microscopy, when you are in a paraxial approximation, let's say, you are selecting only the beams which are propagating closer to the optical axis of the microscope. So this is more or less what she is doing now. So she inserted a small condenser aperture to select only the central part of the spot.
Yes. I changed the camera length. And now I'm modifying, or I'm loading some currents in the lens.
So now we are going to have an image obtained not on the fluorescent screen of the microscope, but these are images obtained with the special detectors, like I have shown you in the theoretical presentation. either the annular dark field detector or the bright field detector. So this, what you see here, is already an image at low magnification obtained with the annular dark field
Yes.
detector. So it's an annular detector capturing the electrons scattered at high angles with respect to the optical axis of the microscope.
So
And
it's not,
yes, the signal, so where we have signal means that we have a sample. So the sample appears bright on a dark background. Dark background means no sample.
I am changing the focus to try to observe the lattice fringes. Well, the magnification is very low, but I will go now. Now I'm at 1 million. The image is not so easy to obtain like high resolution, for example, because you can still have some aberration in the image, or the main problem, contamination, and the contamination can destroy the sample and will not be very transparent for the electron beam. It will be very difficult to obtain high resolution STM. We already have something here. We can observe some lattice fringes. But how I said, the contamination can destroy everything.
Yeah, it's not the happiest day with this contamination. It's
Yeah. Well, I will move a little bit. Yeah, this is the contamination.
but this way, this way you have the possibility to see what are our daily problems, and you can see that it's not always easy to get nice results. You have to work a lot sometimes.
Maybe also the sample, it's not in the right orientation, is not in the exact zone axis. Also, this can affect the image.
What we do in such situations when we have this carbon contamination layer appearing, and we do what is called beam shower. So in the microscope, with the sample in the microscope, we increase the irradiation dose by eliminating all the apertures, and we scan the sample on a large area, trying to decompose the now it looks better. Okay,
Yes. Okay.
I will not talk anymore.
Yes, the contamination is big.
So a beam shower means, as I said, illumination at high beam intensity of a large area next or including the area of interest for, let's say, depends on the sample and the contamination degree, for either 10 minutes or half an hour, depends. And you can try to limit or stop it, I mean the contamination, for let's say 10 or 5 minutes or 5 or 10 minutes, when you can work quietly. You acquire rapidly the images, and this is it.
Yes.
So the contamination is more and more important, or quantitatively, or yes, important, when the beam has a small size. When you use a larger beam, the contamination is not so disturbing, although you still created it, but at a lower rate.
Here I'm at the interface between substrate and strong retinate thin film. these spots are the contamination.
So you end up by decorating your sample with carbon dots like these, large spots.
Yeah. Yes, this is a high resolution STM image, but the contamination will increase and will increase. So I think would be better to stop a little bit, or I don't know what we can do. Usually I have to stop a little bit to make a beam shower, something like 10 minutes. After that, 5 minutes I will work, and after that 10 minutes I will make beam shower, and so on. For eels, for example, we need a clean sample because the edges, the signal in the eels will be inside of the carbon signal. So
What I suggest is to, because I think our guests already saw that more or less how it works. So you can imagine once she has a clean image, she just records it, and
yes,
we can work on it. We could try to pass on showing how the EDS and eels work. Perhaps first eels,
okay,
and then
eels, yeah.
yes, just to
Okay, so I will work on low magnification.
yeah. In this case, the contamination would be
Yes.
lower, and you can because otherwise there are some dead
yeah,
times when we have to we wait
yes,
for the beam shower, and
yeah,
it
yeah.
becomes boring for the
Yeah, of
assistants.
course. Okay, so I will start with eels. I will work on this image at 1.5 million magnification, and I will put the beam here in this area. So in this moment, the beam is fixed, is not scanning. So I will, let's see how a spectrum can be. Okay. The zero loss peak, it's a little bit, okay. Here is, this is the zero loss peak.
So as you can see on this image, the spectrum has a very important feature, this zero loss peak, which is the most intense part of the spectrum. This zero loss peak is the peak determined by the electrons who cross the sample without interacting with it. So they keep their initial kinetic energy, and as I told you, this is the most intense feature of the spectrum, and we use it to focus the instrument. in order to get the highest resolution in the chosen working parameters. So typically the resolution is below is around 1 to 2 electron volt. In the specification, it is mentioned as 0.7 electron volt. So we are not in the conditions of XPS where you have milli electron volts resolution. So here we are at this level, about between 1 and 2 electron volt, with the best adjustments that we can do, reducing the filament emission, and finally focusing the beam, we can get to the 0.7 electron volt spectral resolution.
Yes.
And then what we see is a big bump here, which comes from so in the first tens of electron volts we have the plasmon peaks, and then on the tail of this spectrum at lower and lower intensities, as we go to the right side of the spectrum at higher loss energies, we have the signals, the absorption edges corresponding to the core levels of the elements in the sample. So they are not visible at this because there are a few orders of magnitude difference between the zero loss peak and the spectral features of the elements. So we only use this whole spectrum containing the zero loss peak for the to adjust the spectrometer. And then we have to move and to take off this zero loss peak. We take it off the CCD camera, and we concentrate, we focus on the absorption edges of the elements in the sample.
So I shift the energy at 400 EV. And let's see. Okay, we cannot see anything here. I will increase the exposure time. Okay. Here it is titanium, near have to be oxygen, and somewhere here have to be barium, but I'm not in the our problem with contamination.
I think you should keep the scanning on, because this way you avoid contamination. And
oh, look.
okay, so now, because these are the contamination traces here,
Yeah.
but the dark, the white spots, and now you can see the small features of the absorption edges of different elements. So you can perform this yield spectrometry, this kind of spectrometry, either on a fixed beam. You go to the beam on a precise spot, and you start acquiring spectra, or you can perform it onto an area, a limited area, and you can acquire simultaneously an image and a spectrum, and you can combine them in so-called spectrum image. So what she did here, she acquired a spectrum from across the whole sample, I guess. I don't know. I didn't pay attention.
Yes, for all sample. Here
Okay.
we have titanium.
So as you see, the spectral features are just small features on the tail of the signals that we have at lower energies. So these lower energies are something like a background on top of which we have the useful signals that we have to extract now. So
Yes.
we have to eliminate the background, and this is how we obtain the useful signal. It's the signal which goes above the
Yes.
the background.
We have titanium here, oxygen here, and barium here. So this is our signal.
Okay, so this is an example of a spectrum acquired from a certain area, and so
Yes.
you can do it either working in STEM mode as we are now here, or you can perform also EELS in the TEM mode, where we don't have this problem of contamination anymore, but the localization is poorer, because here with a focus beam you can concentrate onto really small onto a really small area, while in TEM you cannot do that. You have to select an area, and as I told you, that selected area is not always as small as you would like to. Moreover, in STEM, as I told you in the presentation this morning also, you can combine the two modes, imaging and spectroscopy. And you can acquire a set of data, a data cube, containing both imaging information and spectroscopic information, so spectrum imaging. And you can do that at higher magnification, at atomic spatial resolution, and you can indeed obtain, you can now here she is getting
A better one.
better spectra.
Yes.
So you can do that with an atomic resolution, spatial resolution. So you have your structure resolved both spatially and chemically. Very important when you analyze interfaces, or I don't know, core shell structures, and you want to show what is yes, the nature of the interface.
Okay, I lost
But it's
it.
not always easy, as you can
Yes.
show, and especially this is a visit effect. When you have visitors, sometimes it doesn't work. And
Okay, I will save this.
so you can identify the spectral features and say that, so you can identify the chemical elements in the sample. You can perform quantitative analysis, which is not the most, let's say, precise quantifying method. Here the precision, the quantifying precision, it's you cannot guarantee less than 10% accuracy when detecting the chemical composition of a material, because the quantifying technique is based on counting the electrons which are above these background, as I told you, and you have to make use of atomic models that have to approximate the shape of these spectra. And it's not very easy to do that. As a matter of fact, EELS is not used as especially for this capability of quantifying chemical elements in a sample, but it has this incredible advantage of combining, of getting information at a very precise locations. So the local character of the eels and stem eels is the most important characteristic of eels and stem eels.
Okay, we can move to EDS.
Yes, while I will speak also about the fact that you can also detect some chemical shifts. So as I also presented in the spectral, in the theoretical presentation this morning, you can reveal a chemical shift of the absorption edges and determine what is the oxidation state of your element, if it's a pure metallic or a different oxidation state, and this can be done in eels with a nice local precision. And now they will pass to EDS. So for EDS we use another computer, which is now the whole system contains 4 computers, and the eels and the image acquisition uses 1 computer. For the EDS we have to move to another computer that will be connected now to Zoom in order to make possible the screen sharing. Meanwhile, I think I can show you some other, if it takes a bit more than expected. Sorry. I will try now to open one such spectrum image that I recorded for some for CERIC users last year, and I will show it to you. Just one moment. Okay, so I will try to share the screen now. Okay. Come on. Okay, so I hope you can see my screen now. So what we have here is a stem image acquired on a double perovskite. I will make it this way. On a double perovskite, which was barium lanthanum cobaltite, barium lanthanum cobalt 2 oxygen 6. So this is the high resolution stem image, and we wanted to evidence, if possible, some chemical ordering in this structure. It's a double perovskite, and we wanted to make sure that barium, lanthanum, and cobalt are properly ordered inside the crystalline structure, and they are not randomly occupying the atomic position. And This is why we perform this yield spectrum imaging. In this rectangle here, the green rectangle here, this is the area from which we acquired the spectrum image, meaning that the beam was scanned across each line inside this rectangle, and in each pixel we acquired both image information using the annular dark field detector and spectral information using the EEL spectrometer. And this is the kind of data cube that we get. There is nothing to see in this one for the moment, but it contains, as I told you, spectral information, and in each pixel there are spectra. So I can move these pixels all across the sample, and we can see how the spectrum changes from pixel to pixel. And we can use it to identify the elements in the sample, and moreover, the position of that element in the sample. And as I here you have the whole spectrum, and in that position here at 532 we have the the oxygen absorption edge, and then we have the cobalt, barium, and that lanthanum here in this part of the spectrum. I can show you what are the Raluca, when you are finished and you are ready to go on, you can stop me and I will give you the word. But in the meantime, so as I told you, we can extract the spectral features across the sample, across the spectrum, and we have here the edge of cobalt, which is this small peak, and this one. We have barium next to it, and we have lanthanum here. And we can use these features to obtain chemical maps. So by using these two windows, one window to define the background as a red power law curve, and this edge, this window, this green window to extract the signal. And we can map this signal across the scanned area. So this is a map, a dynamic map, which changes as I change the position and I select other spectral features in my spectrum. So if I select barium, I will obtain some maxima showing the positions when I have a higher concentration of barium. And I can do that also for cobalt. This is again barium, and this is lanthanum. And we can record all these images individually, and we have spectral chemical maps for each identified chemical element. And I will try to open, because I have already prepared these maps. And let me try to open them and try to combine them into a dynamic map cobalt. So for example, with these two maps here belonging to lanthanum and cobalt, we can now try to represent them onto a single image by assigning them different colors. And we can say that indeed we have a chemical ordering, for example, with respect to lanthanum and barium. So the barium and cobalt are on the same position, and this is interleaved with the atomic positions of lanthanum. So we can add another. So it's not that easy to make a clear difference between barium and cobalt, because they are quite next to each other, which is at the resolution limit of the spectrometer that we have. But anyway, if I perform a careful analysis, we are able to. And I had here a map where we displayed also the cobalt, and we could compare this map at atomic resolution with the structural model, and confirm that we have indeed a chemical ordering in this material. We have recently published. I mean, last year we published these results into Acta Materialia. So this is more or less what we can get, but we need a lot of concentration to carefully acquire the data, and then to perform a nice data processing and interpretation before getting yes, publishable results. Raluca, are you ready to?
Yes.
Okay, so I will stop sharing now, and I will give you the.
Asta? Și pe care o ale? Trebuie să fac așa? Da, da. Okay.
This is the other computer where we acquire the EDS spectra.
Yes, we have to change the detectors. We use another pair of detectors. So I have to change to make some settings.
The resolution is not very good now. I don't know why.
Okay, unfortunately, I think the dark field image, you cannot see it because it is.
But you can move it on this screen.
No.
You? No? Okay.
No, because it is on the other computer.
No, it's on the other screen.
Yes.
Can you move it?
Just a second. No. Hide. I will try to use this.
If you could hide also the, I don't know, yes, well, I'll let you work.
Okay. The image, it is on DigiScan.
Ah, okay.
And because of that,
Okay, so
but doesn't matter. I'll put it directly on EDS program. Open. Okay, here I already have something. De ce? New share? Resume. Oh. Știu, dar vezi că m-a scos din nou. Can you hear me?
yes, we do.
It is a problem with screen sharing. If I want to open the analysis station, the screen share is stop.
Okay.
I don't know why. It's very strange. Hai să dăm pe asta la o parte. Idee, asta, ia, dăm voi. Aici. Yeah, very strange. No. I said, which is in there? It's not working with another station.
Okay.
Okay.
So I think in that case, I can also show our guests some pre-recorded samples.
Hai să facem cu chestia aia, să selectăm o arie din screen. Stai că aia nu era altceva. Nu share. Okay. I think will work now.
Okay.
Okay. Here we have on last Friday, I think, some EDS analysis. Okay, let's see how the image to look like now.
So you are live now, huh? Right? Okay. So we are just acquiring a new image now.
New image, yes.
Okay.
Okay, this is our image. Okay. I have to adjust a little bit the image. Okay. 2 seconds. So, oh, okay, I will try another image. Okay, I will introduce the EDS detector now. I turn off the beam and now I'm putting inside the detector.
This is not the nicest image on
No.
the
That's all. I will try to fix it a little bit. Okay. Let's see the signal. Da. Share. Acesta. Oh, nu merge. Lasă așa. I think I have a bad signal, a small signal in.
anyway, for our guests, as you can see, working remotely is not an easy task. In TEM, there are dedicated machines which are fabricated for remote access. Ours is not in one of them, and what we are trying now to do has a serious impact on the working speed of the computers, and we are more or less at the limit. And because it's a discussion inside CERIC about this remote access, we can do remote access only by receiving samples. In a normal situation, like 2 years ago, we received the visit of CERIC users, and they could assist to the TEM experiments. Otherwise, this kind of remote access, while the CERIC users can see live what we are doing at the TEM, is not an option for us, because the instrument is not designed for such working mode. So all we can do is to, and this is how we work, is to receive the samples from our users, and we analyze them during the scheduled time slots, and we send them back the processed data. Now it looks better.
Yeah. But the signal is low.
The X-ray signal.
Yes, I have something like 100 counts. So because the sample is very thin in this.
And the sample tilt, the X tilt?
No, it's very thin.
It's very thin, okay.
Yeah, and because of that, we don't have
enough signal. So,
but we can change the condenser aperture.
And what's the spot size now?
5.
5.
Yeah.
So there are different parameters to be adjusted in order to improve the signal. In EDS, yes, you want to say something?
Yes, we can take just some EDS spectra or something like it's we want to make some maps or something like this because we need more signal for that.
Okay, so you just, for example, you launch an acquisition of a spectrum, and I will...
in different points?
Yes, yeah.
Yeah, I think it would be easier.
So in EDS, unlike EELS, the signal comes from the thickness of the sample. The thicker the sample, the higher the signal. In EELS is the reverse situation. So you look for the thinnest areas for EELS and thicker areas for EDS. Now we are in the thinnest part of the crystal because we try to do some EELS. Normally we should go to a thicker area and increase the signal by, on one side, choosing thicker areas, and on the second hand by increasing the beam intensity.
We can choose points, rectangular, line. I will take some points here in the substrate, in the Transmisson, in the thin pin, and the gold. And the line here with 20 points. And start.
So at this moment, the program starts to acquire EDS spectra from the indicated spots from, so we can have we can perform a chemical analysis in each of these pre-selected spots, or do some line profile, composition line profile, and we can also do spectral imaging like in EELS. But for this we need either to increase the signal or to wait for long enough time in order to have enough signal, enough counts acquired.
IN20. Okay. In this case,
we don't see anything. It's just a black square that we see now. This is the spectrum, perhaps. I don't know.
oh yes.
Now we don't see it.
Oh.
No, but let it acquire, and perhaps okay, now it's visible.
Okay, we choose another window. Yes, here we can, in this kind of sample, for example, we can have a problem with the peak overlap. Here, for example, we have titanium and barium on the same peak.
Yes, because the resolution, the spectral resolution in EDS is not 1 electron volt as in EELS, but is 133 electron volt. So there is a high probability of higher probability of peak overlap. And yes, there are situations when the quantitative analysis is not an easy task. And also for the lightest elements like oxygen, and in general up to about Z equal to 11, so below sodium, the signal might be absorbed by the sample itself. It is less probable in the thin areas of the sample because the volume is limited by the sample thickness, so you don't have where to absorb these the X-ray photons. They have nothing but to go outside towards the detector. But you can absorb them into the window of in the detector's window. The detector is not the silicon junction that the detector is nothing but a silicon junction, and this is not exposed to the vacuum of the electron beam of the electron microscope, but it's separated from it with the help of a membrane. And that membrane, a beryllium membrane, sometimes can also absorb the low energy X-ray photons. So you can have some quantification errors due to this absorption of the low energy photons.
Okay. This is the line profile. For example, barium, it is with magenta color, and we can see overlap on the image that where we strontium ruthenate, we don't have barium, but also appear to be in substrate because the peak is overlap with the peak of titanium, which make confusion. So with titanium it's more difficult because how we can see no, barium and green it's the same, have the same profile like barium, of course, because both elements are have the peaks overlapped. Okay, and with ruthenium, I will choose another color. Here we can see where is ruthenium. It's just in strontium ruthenate thin film. And in substrate and in the strontium field. So with this kind of analysis, we can see the elemental distribution on our sample if the peaks are not overlapped, of course.
One more comment when we compare, for example, the EDS mapping and the EELS mapping. In EDS mapping, we have a worse resolution, spatial resolution, when we perform this chemical mapping, just because the useful signal, the X-ray signal, comes from a volume of material. So the thicker the material, the larger the volume, which is a good thing for the signal because we have a good signal. But it is a worse. It worsens the spatial resolution of the mapping. So it's a compromise. If you want to have a good spatial resolution, you should go into the thinnest areas where the volume from which the X-ray originates is smaller because it's limited by the sample thickness. And this is the way how to improve the spatial resolution. But the acquisition is not an easy task because the signal is quite low. On the contrary, in EELS, you are looking for the thinnest areas of your sample, and the resolution has nothing to do now with a certain volume of interaction. It's very localized to the electron beam spot on the sample. So the smallest the beam spot, the better the chemical map resolution. However, nowadays you have performant EDS detectors that have larger area detectors. For example, our detector has an area of 30 square millimeters. But there are detectors with 100 square millimeters or more. And this is enough to capture the X-ray signal even from the thinnest areas of the sample. With our detector, we have a very low X-ray signal in the thinnest parts of the sample. But if we had a larger area detector, we could increase the detected signal and explore also the thinnest parts of the sample, which means that going into the thinnest parts of the sample, we increase the spatial resolution. And at some point, it is possible to obtain, even by EDS, chemical maps with atomic spatial resolution, as we can do in EELS. But this is not cheap. One such detector is more than 200,000 euro. So it's always a compromise between your budget and what you want to offer and to analyze. Yes, it's always like this. That's life in science. Are you trying to do something else now?
Oh yes, I'm trying to map.
Okay.
But I don't know if I will. I'm checking the conditions of acquiring. Okay. I will stop this because I didn't had enough
Count rate.
Yeah. And let's see.
So now she started the acquisition of a map. You can decide what elements to follow and
but even like this is not enough signal.
Yes, so you should spend perhaps 1 hour or more in order to get a map in these conditions.
I
That's why you should normally look for thicker areas or yes, and
I changed the condenser aperture
mhm.
from a smaller one to bigger one, but even like this. But yeah, you have to spend something like 30 minutes or 1 hour if you want to have a good, a nice map.
Because otherwise you can see how the spots started to the
Yeah.
signal started to accumulate, but with not so high
Yeah.
efficiency. Yes, you have to wait a lot in order to build up a map.
But I will stop this because it will take too much. But I have one from last week. I think this one it is. Let's have, this is it for from last week. So in this map we can observe a nice layer of ruthenium here and some small dots of gold here. You can see this, no?
Yes, yes, it's not the best resolution, the best possible resolution, but it's we can still see something.
Yes, and strontium here, but also we have some noise, but okay. And here, titanium and barium are distributed in the same way because of the thick overlap. So strontium, it is where it have to be, and gold here, some small nanoparticles.
Anyway, the spatial resolution in EDS that we can count for is about one nanometer, the best in the best of the situations. So if we want more, then we go to EELS mapping.
Yes. And here it is also line profile.
Yeah, for the gold nanoparticle. Yeah. Well, otherwise, the gold nanoparticle that we see here is some remaining of the external electrode that they applied. This sample came is part of a small device, and they had an external gold electrode, and this is what remained after the ion milling. But if we want to look for a continuous layer, we should go into the thicker parts of the sample.
Yes, and here we have an spectrum extracted from, no, here, this is,
Okay, with the
yeah.
well, we cannot see too many details. We just see the shape of the spectrum, but no, the
No,
labels are not readable here.
okay, okay.
We cannot see which is which.
Oh, okay, okay. Here is gold.
Okay, okay.
I took a spectrum from the middle of the nanoparticle.
Mhm.
Okay.
Okay, I guess this is more or less what we wanted to show you in a direct transmission from the TEM. I guess we should stop here with this, because what I wanted to show you in addition is some small demonstration of image simulation of HRTEM image simulation, and I would like to spend a few minutes for this. So I would like to thank Raluca and Adrian for the demonstration that they performed at the microscope. I know it's not an easy task, so But anyway, so I hope that our guests were able to see, to make an image of how we work at the microscope. So I will try to show you now something about image simulation, as I said. I will just I will launch the simulation software and share the screen. Just a moment. One moment until I launch the... Okay. I hope you can see these two windows that I opened. This multi-guy and image guy graphic user interface. So, as I told you this morning, it is not easy to correctly assign the intensity maxima in a high resolution image to the atomic position in a structural model. So in order to do that, you have to simulate images and to compare them with the experimental images. There are several image simulation programs created either for PC or Apple computers. The one that I'm going to show you here is called HREM, HREM, is designed by a Japanese programmer, and it contains several independent modules. One of them is each of these modules is used for specific tasks. So how these programs work? As I told you, and I think I told you in the presentation this morning, we are using the so-called weak phase object approximation. So in that case, we are able to project the distribution, the electrical potential distribution, the atomic potential distribution, to integrate it across the sample thickness, and to project it into a single plane that we use as a scattering object for the electron beam. So the calculating routine is called multi-slice routine, in which the sample is considered as being made up of several slices with and each slice contains the projected potential of the atoms inside each slice. using the weak beam with a weak phase object approximation. So first of all, we have to define our object, our crystalline object, and we have to create a crystal structure starting from the structural models that we can find in literature. And this program can use the CIF files, the CIF files, the crystallographic information files. And I will use one such file. Just one moment. I have prepared 2 or 3 structures for this demonstration. Just a second. No. Just a moment until I find the, okay, silicon, for example. So I selected silicon as a first example. So I loaded the CIF files. The CIF file, is there any? Okay, so while I loaded the CIF file, you can see here the lattice parameters for silicon, the unit cell parameters, and we can see that we have the silicon atom position defined, and we can choose what is the accelerating voltage that we use, that we work at. Let's put it 200 kV. We can choose the orientation of our crystal. Now, for example, is the 001 orientation. So we are looking along the C-axis. We can choose to divide our unit cell into several slices. For example, for the moment, we leave it for 1 slice per unit cell. And with this information, we save this into a file, a worksheet defined by the program, and we can choose, let's say here, for example, to put into a new folder. Let's say silicon 001. Do you see this? I don't know if you... okay. And then after we save this worksheet defined by the program, we can execute the so-called multi-slice. So it's what the program is doing now is calculating the intensity distribution at the exit of the crystal, and I'm not sure if you can see what this window here. I'm trying to. I will try to add some more windows to this screen sharing. So I will stop the share and I will start again. Do you see my whole screen now?
Yes.
Okay, great. So after I executed the multi-slice calculation, I can save this result. Just a moment, because I don't think I did the right thing. I'll start over again. So I will save this into Silicon 001. Okay. I will perform the calculation and I will show you what are the files that it creates when it makes the calculation. So this is as I go through the program, it creates some files that it uses for the next routine here. So again, execute multi-slice. So it created it performed the multi-slice calculation, and it calculated the intensity, the amplitude of the electron wave at certain levels within the sample, and we can save this. Okay. And now we go to the next. So what I forgot to tell you here is that we asked the program to calculate the amplitude distribution of the electron wave for up to 20 slices. So it calculated the intensity, the amplitude distribution after each such slice, and we will be able in the end to see how the high resolution image looks after one slice, after 2 slices, 5 slices, and so on, up to 20 slices. So this is how we work with the thickness of the sample. We define the sample thickness by choosing a number of slices for which we want to make the calculation. And then after creating this, we go to the next step and we give the program the experimental parameters of the electron microscope. So here we have I don't know if I see some message in the chat, but I'm not sure if it's for me. I don't know. So we have to add some experimental parameters concerning the electron microscope, the aberrations of the microscope, and I have mentioned them here. And then we can ask him to make calculations, image calculations, for certain specimen thickness and for certain values of the objective lens defocus. So we can choose here, for example, to make the image calculation for slice number 5, slice number 10, 15, and 20. Each slice has a thickness of 1 unit cell. One slice is 1 unit cell, and 1 unit cell means 5.4 angstrom. Also, we can ask the program to calculate images for different defocus values, and we can choose, for example, there is a notion of there is a certain optimum defocus value called the Scherzer defocus. So I will choose to, I will ask the program to make calculations from 0 defocus up to the Scherzer defocus. The Scherzer defocus depends on the accelerating voltage, and for 200 kV accelerating voltage, the Scherzer defocus is about -42 nanometers. So I will ask it to make some calculations for 100 for 10 nanometers. Here we are in angstroms. So for 20 nanometers, 30 nanometers, 40 nanometers, and let's say 50 nanometers or 500 angstroms. So it will perform calculations for all these parameters here. I will save these data first. Okay, so I have to select first. I forgot to do this. I have to tell it what structure it needs for the calculation. So okay, so now we will save this. Let's name it Silicon 001 worksheet 2. Save. So he created these two files, and we launch the calculation. So it finished the calculation successfully. It created some additional files that will be used now for displaying the images. Save. And for displaying the images, we use a different routine, which is called image bitmap here. And we open the last created file. And now here we can generate an image for, let's say, by default it's the first calculated image. It's the image corresponding to slice number 5, with a defocus of 10 nanometers, minus 10 nanometers actually. And we can generate this image, and it looks like this. So this is a calculated image for silicon in 001 orientation. We should compare this image, for example, with the model, with the structural model of our material of silicon, for example. And we are one-to-one, one unit cell and the image corresponding to one image cell, one unit cell. Let's try to calculate for another defocus, and we put here, I don't know, 300, the same thickness, and we say generate. There's not much difference between them. I'll try to go to a higher defocus value, minus 50 nanometers, generate. And if we are looking now at these three images, and let's look at the corners, we see that here we have a bright spot, while here at 50 nanometers defocus, we have a dark spot. So as I told you, while playing on the objective lens defocus, we can completely reverse the high resolution, the contrast of the high resolution image. So it is only by high resolution, by image simulation, that we can come to a conclusion regarding the intensity distribution in an experimental image, because we are never sure of the precise conditions in which the experimental image has been acquired. We have no idea about the thickness. We can just have, I don't know, a slight idea. We go into the thinnest areas, but nothing more than that. And we have no very precise information about the image, the objective lens defocus. Although on the control, the software, on the software which controls the microscope, we can see a value, but the effective defocus value is not only a matter of objective lens excitation, but also it's a matter of z position of the position of the sample with respect, the physical position of the sample with respect to the objective lens. So this is why the effective defocus value is still an unknown, and we can only approximate the value by comparing simulated images with experimental images. We can choose to generate the whole set of images for the whole set of sample thickness and defocus, and put them into a tableau, a matrix like this, and it looks like this. And we have a quicker view, and we can compare the simulated images with the experimental. I don't have now an experimental images image on silicon, but only by comparing we can come to a conclusion that we might be. Silicon is not a very complicated material, so you can easily get confused. For example, you can confuse perhaps this image or with this image. So, but this is less important. The idea is that you can, in the end, by comparing the structural model, the simulated image, and the experimental image, you can come to a conclusion that on the experimental image, the bright spot corresponds to an atom or the space between the atoms. Let me try to show you. Well, of course, we can increase the number of unit cells for the simulated image, and we have an image which looks more like the experimental ones because you have larger areas, but that's not important. I would like to show you some other example on PZT, for example. Or we can also choose to examine another orientation in silicon. But I don't think I have too much time left. I don't know what to do anymore. I will try to rapidly show you how it looks for PZT, for example. And I will load another CIF file. So I loaded the CIF files for a file for PZT. We have we have the atoms in the atomic positions here. We work at the same accelerating voltage. We choose to work with the same number of slices, up to 20, and we save this file into a new folder here, PZT, for example. Save. So we have this file created here now, and we do the multi-slice calculation. So it did it successfully. We save this file also. We go to the next step where we select the PZT created file. We use the same parameters for the microscope, and we start. We save this, and afterwards we do the calculation. Save, and now we execute the program. Okay, so it worked. We save this one also. So save. We can close it, and now we can see how the simulated images look like. So open the files that we created in PZT. Okay, again, for example, if you choose to image only one unit cell, for the thickness of 5 slices and the focus of -10 nanometers, we generate the image, and it looks like this. This is how the structural model looks like. And now we are supposed to compare the experimental image to the, oh no. To the structural model. But if we modify the defocus, we see that we have a completely different aspect of the intensity distribution in an image. So let's try to generate all these images and put them into a matrix. And let's try to increase the number of unit cells, perhaps 3, let's say. And this is the image that looks more like with what we can see in the experimental images. Especially these look very much like the experimental images. So this is how we can estimate that the images that we most usually record are obtained under these conditions for a defocus of -30 nanometers, for example. And we can compare these images with the structural model, and we can see that the most intense, perhaps if we go at one cell. So we are in this condition here that we compare with the experiment, with the structural model, and we can say that the brightest spot belongs to the lead atom here in the middle, and we have the zirconium and titanium atoms here, and oxygen on the faces. So I will not go any further because the time is off now. I wanted just to illustrate a little bit how we can simulate high resolution TEM images that we compare with the experimental ones and decide over the significance of the bright spots that we see in the experimental image with respect to the structural model and the experimental image. So this was more or less what we wanted to show you in this practical session. I'm not sure that I managed to convince you, but it's not an easy task to work while explaining. And in case you have other additional questions, I could answer them right now, or if you choose to ask additional questions via email, I will gladly answer them as you wish.